Hello everyone, my name is Meng Wang. Now I'm recording homework 10 of probability and stochastic process. Now let's look at the first question. From my lecture notes, page from 1 to 15, collect the definition and simple properties of examples of stochastic process. The first sub-question asks us to get the definition and properties of Poisson process. For Poisson process, the probability of it is the number of calls received in time t, where t is a fixed number. When this number is equal to k, the probability of it is like this. But now we assume t is not an unfixed number. Then the number of calls received in t is a function of both t and epsilon. So it is a stochastic process. We define Poisson process xt as the follows. When x0 is 0 and x of t1 minus x of t2 equals the number of calls received in time t1 to t2 with the probability like this expression. So this is the definition and property of Poisson process. And for Poisson process, we can use it to calculate the arrival of calls, the arrival of customers, and the queuing theory. Like we could use it to model the number of calls that we received in a time period from 0 to t, or the arrivals of the customers arriving in a store from a time period. The second sub-question is about Poisson increments. The definition of Poisson increments is with x of t, a Poisson defined above, and epsilon is greater than 0, a given constant, we construct a new process. Yt is equal to x of t plus epsilon minus x of t over epsilon. For this increments, the eta t is equal to lambda, and the autocorrelation of it is lambda squared when the absolute t1 minus t2 is greater or equal to epsilon, and is equal to lambda squared plus this term when the absolute of it is less than epsilon. My understanding for Poisson increments and process is that the biggest difference between these two is Poisson process is a process happening from 0 to t, and the Poisson increments is a process happening from any interval from t to t plus c. The third term is Poisson impulses. The definition of Poisson impulses is we define a stochastic process Zt as follows. Zt equals the derivative of xt, which is the limitation of yt when epsilon goes to 0. We could draw a diagram of zt and t. This is the impulse, and the mean of zt is lambda, and the autocorrelation of zt is lambda squared plus lambda times delta t1 minus t2. And the fourth term is semi-random telegraph signal. The semi-random telegraph signal is xt is equal to 1 when k is even in 0 to t, and it's equal to minus 0 when k is odd in 0 and t. So eta t is e to the order of minus 2 lambda t, and the autocorrelation of it is e to the order minus 2 lambda absolute t2 minus t1. And for random telegraph signal, we define alpha to be a random variable independent of xt with probability of a equal to 1 equals to the probability of a equals to minus 1. So we could form a new process yt equals a times xt. Then yt is the random telegraph signal. The difference between the semi-random telegraph signal and the random telegraph signal is that if xt is a fixed one, then we call it a semi-random telegraph. And if x of 0 is a random variable taking 1 or minus 1, then we call it a random telegraph. Now for random work, the definition is given as follows. X of nt equals ks minus n minus k times t, which is equal to s times 2k minus n. And xt is equal to x of nt for nt is less than t and less than n plus 1 times t. The probability of x of nt equals to lambda s is expressed by this term. And the eta t is equals to 0. The autocorrelation is the mean maximum of n and m times s squared.